Wow, I'm so excited to be here. And today I'm going to talk about Redux, but with the Ruby. And this is my first time to be in a conference, Ruby conference in Taiwan, but also the first time as a speaker, so I'm kind of nervous. And luckily, there's no many audience here, so I'm going to do it slowly, and I hope you guys can enjoy the functional program with me. Oh, wait. So, my name is Juin, and I'm a back engineer from iCook. And today I'm going to talk about functional programming. And perhaps some of you have used functional programming or have heard of it. I believe there are so many resources to learn functional programming on the web. And actually, you can just type in functional programming on YouTube, and you can search a bunch of them. But I think maybe the best way to learn functional programming is to use it to build something useful. So today I would like to demonstrate how to build an architecture like Redux, but in a step-by-step way. And meanwhile, I'm going to introduce the related concepts. So here we go. So first of all, I would like to introduce the basic concept. So what is a functional programming in a nutshell? Well, it's a programming paradigm, which means it's a way of organizing your program. And it's so different from imperative programming. Like Ruby is an imperative language. But, well, it has some features to let us to do function programming. Here, I just list some of the features. So first, functions are first-class citizens. This means that functions can be defined and passed as arguments and be returned as a result of other functions. And secondly, functions do recursion to repeat computations. And again, this is so different from what we learned and familiar with, since we use each or while loop to do the daily job. So recursion can also be used to define data types, and it is called recursive data type. And thirdly, functions are pure. Well, pure means no side effects. And a pure function will always return the same output for the same input. Again, this is different from what we do in Ruby, right? And Ruby is designed to be an O language, and O design means to mutate the state of an object. And thus the output of the O method depends on its internal state. This behavior is different from functional programming design, which data is usually immutable. So why should we care about this? Well, functional programming exists for like 50 years. Why does it become popular only recently? I guess there are some reasons. And perhaps the most important reason is that immutability is amazingly good for a high concurrency application, since immutability guarantees that the consistency of the data, no matter how many times it is accessed. Besides, pure functions are easy to test, since it always returns the same output every time. It is always hard to build a large and complex application software. And although we need to understand the design pattern to really deal with the complexity of design. But in functional programming, function composition is the way to control the complexity, but in a more flexible way. And you might wonder, why do I choose Redux as a topic? Well, Redux is a popular JavaScript framework in React Stack and for front-end development. And actually, there are some many guys. See, just actually one of the speakers here, who also invented some framework, like rebuilt React in Ruby, which is cool. So it is used, Redux is used to manage the state of React components. But from my point of view, I think Redux is essentially an observable object tree, but with a single interface for updating its state. And it provides a flexible event handling mechanism. Well, the definition is lengthy, but just look at the picture here. So basically, you have this is an object, right? This structure here, and it provides some interfaces here, like a subscribe, the word is little, subscribe or dispatch, to interact with the object, and make it observable. And I was especially fascinated by its subtlety and usability. And most importantly, these are achieved by the use of functional programming. This is why I choose to review Redux. So I'm gonna build it in the 3 steps, okay? And, sorry? Yeah, sorry. So I'm gonna build it in 3 steps. We'll start from the basic, a reducer. Reducer is the building block of Redux. And it takes a state and an action and returns a new state. It defines how the object should update its state. Okay. Then, in order to express more complicated structure of state, we need to develop a way to organize multiple reducers to construct a single new reducer. From the outside, the new reducer just looks like the original one, like what we developed in step 1. So, which means it also is a function, and it has like a defined input and output. And additionally, we need to find a way to store the state, to keep the state, and it must interface to update the state. And finally, we'll make what is built in step 2 more capable of dealing with different kinds of actions other than just updating its own state. For example, you have asynchronous calling, right? So everybody is dealing with that. So actually, I have built this framework. So what I'm going to do and talk about is open source. You can just check it out on GitHub. It is called Redux. And you can read its spec to see its functionality, or just browse the source code to see what's happening under the hood. So yeah, let's begin. So the building block of Redux is the reducer. So what is a reducer? Well, it's a function, really, but it's more than just a function. It must be able to pass as arguments. It's a lambda. Wow, lambda sounds cool, right? So what is a lambda? Well, lambda comes from lambda calculus, actually. And it is essentially an anonymous function, which means functions with no name. And lambda is a first-class citizen, which means it can be defined anywhere, and can be passed as parameter, and can be returned as a result. So lambda is the foundation of higher-order functions. I will show you what does that mean. So here I give you an example. So in Ruby, if you want to define a lambda, just use the rightward arrow. I mean, there are so many ways to define lambda in Ruby, but I prefer this one because it looks more clean. Yeah. So to define a lambda, just use the rightward arrow and followed by arguments and a callback. And to call a lambda, you just use the dot, and or a call dot, a call. But I mean, the dot is simpler, right? And we can assign this lambda to a variable, and we can pass this variable to other functions. And furthermore, a lambda can be returned another lambda. This is called higher order function. So let's implement the reducer. Yeah. And the implementation is easy. So it's nothing but the lambda. The reducer defines how to renew the state depending on the action type. So it has switch case structure to decide what to do. Given a state and an action with a key type, a reducer has to always return the same result. It has to be pure. So let me explain. And you see the lambda structure here, and we have to define two inputs, state and action. And the action has to be a Ruby hash, but in JavaScript, you have to define it as an object. And you can see that we need to case this guy here and decide what to do, how to update the state. For example, if we have an A+1 action type, then we need to add 1 on the state of A. Yeah, so that's how it works. And here's how you could use this reducer. So basically, you just call this function, right? But call this function with the initial state and an action. So if you pass in A with the type A+1, then you can get the result like if A is gained by 1. So it is easy. And then in the next step, now we have a building block, which is reducer. Reducer itself is just a function, but it's also the data, okay? But it will not be useful if we can't build more complicated data structure. So in this step, we are going to develop a way to organize multiple reducers to create a new reducer. So the new reducer will just look like a tree, and it is a recursive data type. Oops. So what do we mean by a recursive data type? Well, it means that if a type refers to a type for values that may contain other values of the same type. For example, a binary tree, the picture here shows that, well, each children is also a binary tree. So it's kind of defined itself by itself. Yep. So, well, here's the way to implement a binary tree. And there are two types of nodes. As you can see, two classes. One class is node, and the other class is empty node. But, well, you don't have to hear about the detail, but what I'm going to show here is that the similarity between the tree and the reducer. So here's the reducer, right? You also have two types. And this is so close what I just showed you in my previous slide. It also has two types, right? Native and combined. But this is really complex, right? And actually we can make it simple. We can make it simple. Let me show you how. So let's really think about the tree. And how can we just implement simpler version? Well, we can just, the thing here is that we only wanted to express the hierarchy of the data itself. So we actually don't need methods for manipulating data. For example, you want to traverse through the tree or finding its children or parents. We don't need that. So this implies that the distinction between the node and the empty node is not necessary. As a result, a hash is already sufficient to express the data hierarchy. So we need to implement a function to merge multiple trees to a single tree, which is nothing but a hash. So in my code, I just defined a simple merge, and it returns, like, it takes the left tree and right tree and the element, and then somehow I just return a hash. But as I said, a hash is a tree, right? So I created a tree inside, and left is defined the left, and right is right? So I can just use the merge here. So the same logic just applied to reducer. So I can just have another method called combine. So the function combine will merge multiple reducers into one single reducer, just like a tree. So if we call this new reducer, the return state will have the structure corresponding to the way we organize reducers. And what do we mean by that? Well, this means that when we take a hash of key and reducers, right? And then I return a function, which not surprisingly is a reducer. But inside this function, I need to define how to organize this data, right? So what I did here is just, I just extract the key and I just map through these reducers. And there's a key and reducer, right? And I just pass the state itself and the action down one level. So it's like I pass the action object down to its children, and then I just collect its new state result, and then I pass back and convert it back to hash. So this is simple, yeah. And this is one example of how to use that. So the important part is here. So now we have a combine function, right? So I can combine arbitrary numbers of reducers and just merge into only single one. Then I provide a key, is filled, and well, its value is another combine. So it's like recursive, right? I can just keep going, and have a really complicated structure. And as you can see, that structure of the tree is like corresponding to the way I designed it, which is useful, right? I can just express any kinds of data. Okay. So actually, in step 2, we have to do one more thing. Like reducers are pure functions. It means, well, they are stateless, no state. So in order to store a new state whenever the action is applied, we need to design kind of a wrapper that stores the state. So we call this wrapper a store, right? Clearly, the store stores the state, so it means store. So additionally, the store exposes its interface for calling the reducer. The interface is called dispatch. Okay, and instead of passing actions to the state to the reducer directly, we can just call dispatch with the action. And the dispatch function will automatically pass the action and the current states inside the store. And store also has another interface. It's called subscribe, which is used for subscribing functions that are going to be called after the state is updated. And this makes the object observable. And what I show here is that, well, previously we have this structure, right? Reducer tree. But it's not that convenient that we have to find a way to keep the state, or else it's not going to be useful, right? So it's kind of like we design a wrapper, and inside this wrapper there's a local state, local variable called state. So whenever you just pass in a state in action, it returns a new state, and store just somehow keep it. And in order to use this reducer structure, we just need to call dispatch, right? Dispatch, you don't need to pass in a state. So if you call dispatch and the state, he just grab this state for you and apply it to the reducer and return a new value and store back to the state. And here's this function subscribe. Well, I said observable means that whenever this object is the thing we want to observe. So whenever it gets updated, we should just call some other guy and say, hey, I'm updated. And this is what subscribe do. And yeah, finally, we're going to enhance the ability of the store and make it capable of handling all kinds of actions. The store now can only handle actions with certain payload. What if we need to get the data from somewhere asynchronously? This asynchronous operation cannot be performed in reducer. Since reducer has to be pure, means you cannot change the state of the outside world, right? So we need to design another mechanism to handle this kind of action. And in Redux, it is called middleware. And conceptually, it is really similar to Rails middleware. And middleware is built on functional composition. And composition is perhaps the most important concept in functional programming. So what is composition? Well, it's nothing but just you apply something to a function and you just apply this to another function as input, and that's a composition. So you probably feel more familiar with the mathematical definition. So by the use of composition, simple functions can form more complicated functions. And on the other hand, complex functions can be split into smaller functions. And this is extremely useful for program design. So let me give you a working example. So here we have two functions, and they can be composed to another function. This is good. But what if we have more than two functions to compose? Of course, we don't want to do it every time when we need to compose another new function, right? So what can we do? Well, we can have this kind of program, right? Now, instead, we can abstract the compose logic and make it reusable. And to compose a collection of functions, we can iterate each of them and apply compose function until every function is applied. But there's a problem. The way we approach this problem is not pure, right? Since we have a composed local variable here, but actually inside this iteration, it's just get updated every time. This is not pure, right? So what we need to do is we have to figure it out some way that you cannot change the state of outside world. So can we do it? Of course we can. We can do it more concisely and elegantly. And now things start to look like functional programming now. Yeah, let me explain this for you. So here we just use one of the Ruby's magic, the reduce method. What reduce does is it takes an initial input as a first result. Then it traverses the collection and recursively computes the new result based on the operation defined in the block. And you can see that in the block, this is what the real business happened. Because I just put whatever the result and thus the input to the current function, which is just compose, right? In compose, we define the result and it's just applied to another function. So this happens recursively. And the computed result and the current traverse element from the collection. So in this way, the composition can be done if we wrap the function to be composed with an extra parameter f, where f here is just the result of previous composed function. And the reduce should be performed reversely to meet the order of the collections. So I just showed you the essence of function composition. And this is exactly how Redux implements middleware, and I think this is really elegant and concise. Okay, so here's just implementation, right? So here I have a similar stuff like the one I defined in the previous slide. So I have to create, and you can see the structure here. The next local variable is just the f. It's just the f I defined, right? And the compose again. Well, it's the same, right? Here. So you can see the similarity between these two lines of code. So the only difference is that instead of I define an init local variable, I rather pass in another value here. So then I can just use it inside here. And finally, apply. So yeah, there are some other things happening, but the actually working part is here. Compose, and you have a chain of middlewares, and then you pass in the initial value, which is just a dispatch, and then done, right? So this is usage. Well, I can create two different middlewares, right? And then I just somehow apply these two middlewares, and then assign that into another variable, new dispatch. And then if I use this dispatch, then things behave different. But previously, the dispatch will just apply to the reducer, right? But now it has to go through these middlewares. So if I just call this new dispatch, you have to go through put middleware 1, and then put middleware 2, and then do the stuff, update the state, whatever. And then it goes out, inside out. It's like onion, right? So here it prints an out middleware 2 and out middleware 1. Well, this is really confused. So let me show you how to do that. Okay, so here I set up. So this is what I wrote previously, and I have predefined some reducer. So this is nothing but a function. So important funny part is here. I have a combine, right? So I combine, and there are two keys, foo and bar. And then the value is another combined value. So A, B, C, D, E, F, G, H, G. Yep. And middlewares, right? I just defined two middlewares. Yeah, it's a function. And then I apply these middlewares to another variable, E, and then somehow create a new store. I mean, the store is a wrapper, right? So I just apply this reducer and the enhancer to the store, sorry. And one last thing, whenever I update my state, I need to subscribe something to happen. So I subscribe two functions. As you can see, it's a lambda, right? So whenever it's updated state, the lambda will be called, and then the process is over. So what does it look like? Well, if I have a store here, yeah, the store itself is just a Ruby object, and I have a dispatch here. And I have the reducer state, and I want to check out its state. So I just .state. Let's make it more prettier. Yep. So this is a structure I just designed by the combined reducer. As you can see, that's just like a tree. And now it has some initial state. You can see that the A's value is 1, B is 1, right? What if we just dispatch? Store.dispatch. And remember that dispatch is a new version, so it has to go through the middleware, right? So I just dispatch in action. Let's do it like C+1, okay? So it's type C plus 1. Okay. Yep. So you can see the result. It has to go through middleware 1 and then 2. And then the subscriber is called. So it prints I'm called 2, and now the middleware. And it returns the action you passed in. Yeah, that's basically how it works. So, yeah, I think I'm running out of time. And just a few messages. What I've covered is that I explained some really basic functional programming concepts like lambda, like recursive data type, like composition. But there is a whole bunch of concepts that I have no time to explain about, which is like immutable. What does that mean to be immutable? And one is lazy violation or even monad. Yeah, this is a magic word. I don't know. If you write Haskell, you know this word. So I hope this talk inspired some of you, and perhaps we can contribute to Redux together. So this is the end of my talk. Thanks for listening. And any questions, welcome. Yeah, please challenge me. Yeah, please.
Are there any immutable data structure available for Ruby?
I guess so, because I think there's a gem called Ruby Immutable or something like that. You can just Google that. Yeah, but I'm not really understand the internal working principle of that. So yeah, and you can use freeze, I guess. Yeah, just freeze the object. Yep. Anything else? Okay, thank you very much.
Thank you.